OK, I have one more path searching algorithm I want to show you, and it's pretty similar to Dijkstra's algorithm. It's called the A-star search. And I got to say, I have a real fondness for this algorithm, because a long time ago, I discovered it. I was in college. I was kind of early on. I guess I was a little farther along than you guys, but the course I took, the equivalent of 106B, didn't happen to cover graphs, so I had not heard of this algorithm yet. But I was writing a Pac-Man game, and I really wanted to make the ghosts be smart so they could chase you down and kill you. And it turns out this algorithm, I mean, path searching, that's what that is. Like, the ghost is here, and Pac-Man is there, and there's walls. It's a maze. I've got to figure out the right way to go to eat that guy. And I didn't know it at the time, but I needed this algorithm, and I was like looking in books and reading, and Google was kind of a glimmer in Sergey Brin's eye at the time. So I was like learning this stuff on my own, and I discovered this algorithm, and I coded it up, and it worked, and I thought it was super cool. And so it's kind of a treat for me that now I get to torture you with it. In fact, my Pac-Man game is still up. I don't know if I can get it to run. I mean, I can't even get a Trailblazer demo to run. You have your hand up. What were you going to say? Yeah.
Were you the first person to think of this? Or did you
No, sorry. I didn't discover the algorithm, think of it. No, it would be called Marty is a Badass Search, if that were the case. You better believe if I ever invent an algorithm, I'm going to name it after me. No, what I mean is I discovered that this algorithm existed when I was searching for something to use, and I said, oh, this is just what I want. I got really excited because I thought, I'm never going to, Pac-Man's so specific, I'm never going to find a Pac-Man algorithm tip anywhere. But I discovered, no, this is like a very general problem. I was just learning my CS, and I thought, I will never find anything that will help me code this. This is really hard. And I was ecstatic to find that there was an algorithm just for what I wanted to do. And I wrote it up, and with a few tweaks, not twerks. After a little bit of twerking to rest, I coded the algorithm, and it worked out. Let's see, is it still martystep.com/pacman? The thing is, I don't know if it runs on my browser. Allow? I don't know if it's going to run or not. My ICE-T web? What the heck is that? Is it running? It might be. Hey, it's running. Cool. You see that red fucker down there? He's using that stupid algorithm, which is why he's always on my ass. And you know what else? Watch this. You know how he gets back his little eyeballs to the cage? Same algorithm. Anyway, I'm a little more proud of that than I probably should be. Yeah, I coded this thing from scratch. I'm pretty happy with it. You can even switch to Ms. Pac-Man, and now I've got a little bow on my head, right? And anyway, okay. But that's not the point. I mean, I made this a long time ago, so I have to brag about the only thing I've actually gotten to work in all that time. So A-star search is definitely baked into the code of that Pac-Man game, and A-star is basically a modified version of Dijkstra's algorithm. And let me try to explain the justification here. So Dijkstra's algorithm is very good at what it tries to do. It looks at the weights. It finds the cheapest cost path. Now, let's think about how it really works for a second. It uses a priority queue. And that means it looks at the cheapest cost vertex that we haven't visited yet, right? Okay, and that's probably a good thing. So what I'm trying to draw in this picture here is that Dijkstra's algorithm considers what I would call the known distance. We're trying to find a path from A to C that is the cheapest. And Dijkstra's algorithm has a PQ that is sorted by, I started here, and this is the part I'm at so far, and it has this cost or distance so far. And the cheapest one of these is going to come out first out of the PQ, okay? But after the point that I've reached so far, there's going to be more to get me to the destination. And I don't know how much that's going to cost. It is possible that a path with a very low cost here the cost that we know, the cost that Dijkstra's uses, might have a really expensive cost here, which would ruin that path. It's possible, right? Cheap over there, expensive over there. Who knows why? Maybe it's a maze and I go this way and oops, that makes me take a really long turn to get to the end. Maybe that path was cheap to start but expensive to finish. Something like that, okay? So it's too bad that Dijkstra's algorithm only incorporates that into its prioritization and doesn't incorporate this part. But you might say, well, I don't know this part. I mean, I haven't checked that part yet. I haven't visited that part yet. So that's why I don't know. That's why it's an unknown distance, right? Well, okay, fine. But what if we could estimate the remaining distance somehow? And if we could, maybe that would be something we should incorporate into our algorithm. So let's think about, if we knew a little more about the graph, a little more about the world that we're exploring, that might be information we could use. Imagine that we're exploring a two-dimensional terrain or a maze or some sort of spatial graph where it really does represent moving around, okay? And imagine that it costs a certain amount to take a step. So if I walk, I can only walk in the 4 main directions. So every step costs 1, right? Okay, fine. Imagine I'm starting over here and I'm going to go over there. I'm going to go to the right. Maybe someplace way over here. Dijkstra's algorithm thinks of all of those numbered ones as being equal to each other. Like when I say something has a 3 or something over here has a 3, it thinks of both of those 3s as being equally good in terms of which one would come out of the priority queue, right? But when we look at the picture, if we're trying to get over there, we like that 3 or that 3 way better than that 3 or that 3, don't we? We have more information than Dijkstra's algorithm has in this specific example. Well, maybe we should use that information to help the algorithm. And so I would call it a heuristic. A heuristic is like an educated guess, estimation, speculation, something like that. And if you talk about graph searching and you say, I have a heuristic here, usually what you're describing is you have a function that can give an estimation of the cost or distance from one vertex to another one. Not direct neighbor. You don't have to estimate the cost to a direct neighbor. You just look at what the edge cost is. But the cost to some distant neighbor that you have to walk several steps to reach. Now, in many graphs, it's not really possible. Like in the general case, there's no way to come up with this kind of estimate. But for specific kinds of graphs, like maybe a graph of a map or a maze or something, maybe there would be a way to come up with this kind of a function. Okay? And one property that's really important is you have to never overestimate the cost. It's okay if you underestimate, but you can't overestimate. Why is that the case? Well, I mean, I'm not going to give you a formal proof of this, but basically, if you overestimate, it can jack up the priorities in the queue, and then things come out in bad orders, and the algorithm doesn't find the best result. That's the short answer to that. So if you were doing something like Google Maps, Google Maps, you want driving directions or something like that. And if you look at the 2 points on the map, you know how far apart they are. But you don't know that there's not necessarily a straight road connecting them exactly straight between them, right? You might have to zigzag around a little bit to get from the one to the other. But an estimate of how expensive it will be to get from one to the other would be to just measure the straight distance between them. You could say, well, they're about that far apart. And again, that's probably not exactly the right answer, but it's a decent estimate, right? It's a rough guess, educated guess. And if anything, it's an underestimate, right? Which is okay. So this is our new algorithm that we're going to learn about today. It's called A star. A star does incorporate the remaining distance from the point that you've gotten to so far compared to the destination by estimating it with a heuristic function. And I mean, the punchline here is it's exactly the same algorithm as Dijkstra's algorithm, including you use a priority queue, all the stuff we just walked through last time and today. The only difference is we somehow calculate this value here and add that to the priority before we put things into the PQ. So I think that's written here on the bottom of the slide. The priority of B that it should use in the priority queue, we used to say just make it be the cost, the total cost to get from A to B. But now we will add heuristic from B to C. What's heuristic? Well, it's going to be some kind of function that maybe I'll give you, or maybe you can calculate based on the graph, something that you know about the graph data. So here's an example. Here's an example. I'm searching in a maze, like a Pac-Man maze maybe, huh? I want to get from A to C. If I look at the squares around me, I think the slide, there's supposed to be like a black line right there, like that's the end of a column just here. I can draw it. Oh man, I can't draw a straight line. Okay, wait. Okay, here goes. I got this. Okay, wait. You give me one more try, right? I teach you recursion. I teach you pointers. You clap when I draw a straight line. I love you too. Okay, well, so there's A. I want to reach C. If we were doing Dijkstra's algorithm and we wanted to think of this as a graph, you would just connect squares to their neighbors with an invisible, imaginary edge. You'd say, oh, I can reach you with a cost of 1. I can reach you with a cost of 2. 1, 2, right? 2, 1, 2. This kind of thing. 3. But what we'll do instead is we will try to come up with some value to add to these numbers, which would be an estimation of the remaining cost to get to the destination. What would you use as your estimate? Like, how would you calculate it? Keep in mind, these squares, these like vertex, like if you think of each square as being a vertex, they all have row and column numbers associated with them, right? So how would you calculate a heuristic of the remaining cost? What would it be? What would you use? Just like a straight line would be like Pythagorean theorem, like dr squared plus dc squared, and then take the square root of that, like that kind of thing. Yeah. So just a straight line from there to there. Yeah, and actually, if you would permit me, I could do something even simpler than that. So if I don't want to do square roots and doubles and rounding off and stuff, I could just use what you would call the Manhattan distance, which is like just add the, like just make an L, like how many rows over is it and how many columns over is it? You know what I mean? Like that will work too. Your thing's more accurate, I think, than mine. But I don't like doubles. Int is easier than double. And mine just has to add, or subtract or whatever. So like, okay, instead of considering this square right here to cost 2, let's say it costs 2 plus I have to go 1, 2, 3, 4, 5 squares from there to get to C. In the best case scenario, if there aren't any walls in the way, that would be the cheapest possible outcome, right? So really, instead of calling this a 2, I'll call this a 7, okay? And now this one just to the right of me, it has a 1, but I'm going to say, well, ideally, it would take 2 more to reach the target. So that's not a 1 anymore, that's a 3. This one up here, it's 1, 2, but it has a 1, 2, 3 to get to the destination. So that's what, 2 plus 3, it's a 5. You understand? So you put these in with the sum of those things as the cost. And that's going to impact what order things come out of the priority queue. In Dijkstra's algorithm, these neighbors around me, the immediate neighbors around me would all have a 1, right? 1, 1, 1, 1. But this one has 3 now. This one just above me has what? It has a 1 plus 1, 2, 3, 4. So it has a cost of 5 now, not 3. I'm going to erase. I just don't want too many numbers to be all on the screen. So this one, instead of being a 1, is now a 5, I think I said, right? This one below me, I think by symmetry, is also a 5. This one over here is a 1 plus a 2, 3, 4, 5. So this one is a 5. So do you see what happened? Like if I pull them out of the PQ, the one to the right of me comes out first, which is probably a good thing to do. Now you say, well, there's a wall here anyway. I can't just go straight over. But I might as well try going that way first. If there weren't a wall there, that would be the way that I would want to go. So I go there, and then I enqueue its neighbors. Well, this one's neighbor is a cost of 1 and 2, and then 3, 4, 5. So this one is a 5, and this one is a 5, I think. And you just go from there. Like the one above this guy would be 1, 2 to get to them, plus 3, 4, 5, 6, 7. So these ones are 7s. And so you become less and less likely to go over to the left and go out of the way. these squares up here going way up and above or below the wall, they have a little bit lower, a little bit worse priority too, but eventually you try them because you have to get around the wall. So, I mean, really, this is still doing Dijkstra's algorithm. It's just, switching around a little bit the order that we're going to visit things to sort of favor ones that seem like they're going in the right direction. And you don't always know what the right direction is for just a general random graph that I just draw on the screen. Like a minute ago, that one that had the path from E to H or whatever, and we traced it all out with Dijkstra's algorithm. That's just some random graph that I just made up with fictitious weights and vertices and edges. So you can't really come up with a heuristic for some random graph like that. It has to be something like this, where the vertexes and edges mean something, and we can infer something from the state of what we're doing, OK, anyway, the code for Dijkstra's algorithm, or excuse me, for A-star, I think it's coming up on one of the next slides. I guess this one, this picture here is showing us all the heuristic values that the different squares would have. So it's like the cost to reach it, you would add this number to that cost to get the total priority for that square, I believe. OK. So here's Dijkstra's algorithm code. Watch carefully. Here's A-star code. Oh, wait, it shrunk a little bit. I was hoping that it would stay exactly the same font. That's not very cool. Wait, let's make this more cool. OK, get out of here. There. Oh. OK, there we go. So there's the code for Dijkstra, and there's the code for A-star. So what you'll notice, I'm just going to keep doing this. It's going to get really annoying. The first thing you'll notice is that instead of enqueuing the starting vertex with priority 0, you enqueue it with the priority of its heuristic cost from itself, just straight line from itself to the goal. And basically, that's what you're going to do always. You're going to use what the priority would have been plus what the heuristic function estimates the rest of the cost will be. You're going to do that kind of everywhere. And then down here, later in the algorithm, when you're putting things into the PQ, you don't store them with a priority just of that cost, which is what Dijkstra would have done. You store them with a priority of cost plus what the heuristic thinks will be the remaining cost from the neighbor to the goal. That's it. It's actually really, really similar. There is a really common bug that people have. So if you're like taking notes on that kind of thing, like I'm going to have to answer a bunch of piazzas that ask it anyway, but that's OK. I'll tell you now. A lot of people add in the heuristic up here when they compute the cost of the vertex. Cost equals whatever. They add in the heuristic right there, but you shouldn't do that. The heuristics don't get mixed into the cost directly. They get added to the cost to form the right priority. The reason that you don't want to add those in here is because the costs are still costs, and the heuristics kind of muddle those up, I think. So I'm just telling you, if you add in the heuristic, right here, it's going to mess up the algorithm a little bit. It'll mostly work, but it'll kind of give you the wrong answer, and it'll be really hard for you to debug. So when you come to office hours and ask me why it's doing that, I will say I already told you. And I'll make fun of you for a while behind your back after you leave. But I will help you solve it. I'm just kidding. I only make fun of the section leaders behind their backs, not you. But, oh, I forgot. Some of them are here. No. Anyway, so it's very similar to Dijkstra's algorithm. A person who dislikes redundancy might even try to somehow take advantage of that fact. I will say no more. But anyway, those algorithms are pretty similar to each other. That's all I have to say about A-star. So I guess what I would say to you, though, is the thing that confuses students sometimes is like, where does this heuristic come from? And I guess the thing is, like, whoever put together the graph that you're going to look at, if that graph came from some sort of spatial data or something that I actually know this kind of thing about, then hopefully if I pass in two vertexes to a function, maybe I could look at them and say, oh, you're the vertex from this row and column of the maze, and you're the vertex from that row and column of the maze. So I can calculate your distance, and that's the heuristic. Here you go. So I'm going to give you a homework assignment where I give you a heuristic function that you can just call and you just use what it gives you out. And so you'll just like use that in your algorithm here. But if you were writing something from scratch, you would have to look at your own data and sort of figure out like, hey, is there a good heuristic function here? What is it? And how do I incorporate that into this code? So do you have questions about A star? Like if I show you this picture again, like does it make sense, kind of the difference between the two algorithms? Yeah?
If you should move diagonally, then you wouldn't be able to do the L thing because it would overestimate.
Yeah, she had a good question. Like if this hypothetical example, if I were allowed to walk diagonally, like in one hop, jump from here to here, I guess you can't see on the screen, but jump from here to here in one hop, then would I be allowed to use this sort of L-shaped distance as my heuristic? The answer would be no, because that L would say that you have to walk 1, 2, 3, 4 steps in this case, and I could get there in 1, 2, 3 steps. So I would have to, then maybe your direct line calculation would actually be the only correct one of the two. Yeah, good question. And it is important that you not overestimate. I guess you'll have to take my word kind of for that, because if your heuristic is producing an estimate that's too big, then it means your priority is too big and it pushes you too late in the PQ, and it actually causes you to avoid some good paths and to look at some bad paths first, and then it makes you spit out the wrong answer, basically. Okay. And so I guess if I were going to show you like a little bit more of a visual representation of this, I mean, I showed you Pac-Man, right? And so the ghosts are using A star. The ghosts could have used Dijkstra's algorithm. That would have been fine too. They even could have used breadth first search. A lot of these algorithms are fine. But it actually kind of comes down to like efficiency and stuff. I had a hard time running this demo last time, but let me try it again. Where was that? CD, B, autumn, homework, 7, solution. Yeah, okay. So here it is. And then I showed you this Trailblazer program. And I think what I showed you the first time was I showed you a maze. Let's do this medium-sized maze. There's a maze. And I said, hey, let's do breadth first search from like here to here. That went a little fast, but I'll run it again. It's basically going outward equally in all directions by 1. If you watch it, if you slow it down a little more, you see it goes like 1, 1, 1, 1, 1, 1, 1. Each of the little paths, walks out one more step. So if you look over here, it's a little hard to read the font, but it says I found a path. I had to visit 103 locations to do it. If I switch to Dijkstra's algorithm and I run Dijkstra's algorithm on the same points, you might find that it looks kind of similar to the breadth first search algorithm. And it's very similar. In fact, it produces the same number of locations visited. I asked about that really briefly last time. Do you remember what I said about why they're the same? Why does Dijkstra and breadth first produce the same number of squares visited in this example? Yeah?
There's no cost.
Because the costs are all equal. There's no difference in the cost from going up versus going down, going left, going right. So therefore, the priority queue is not really, all the priorities are the same, basically, in the priority queue, okay, for the most part. That's why those are the same. But what about A star? Now, if you were listening to what I was saying about A star is supposed to sort of favor going a good way versus going a bad way. So if you're going to predict, you'd say it's mostly going to go over to the right and not left and up and down. Let's run it. Boom. So now what you'll notice is it still went left and up and down a little bit, right? It didn't just like go straight to the goal. It's not like omniscient or some shit. It's just mostly going to try going to the left. Why do you think at some point it would try going a little bit up or a little bit down or whatever, like a little bit to the left like it did here? What would cause it to do a little of that as it went along? Any guesses? Any thoughts? Yes?
So doesn't know the heuristic value of those nodes.
Yeah, I mean, at some point what happens is the heuristic value, like if I get kind of halfway going to the right, that's pretty good so far. But at some point, the cost of like one step plus heuristic is less than where we are here. And so the bad paths that are in the wrong direction, it will eventually reach them, but only once their priority is less than other things' priority. So you're going to have to take several steps in the right direction before it's willing to explore a step in the wrong direction. And it just kind of depends on the relative priorities of it all. I also showed you these terrain files. So this is a terrain. Do you remember what I said? That these are like elevation maps, like looking down from the sky, where a light color means like a mountaintop and a dark color means like a valley or whatever, a low elevation. And so if you were searching for a path from like this place right here to this place right here, like from here to here, that's going to take a while. Breadth first search just explores out in a square because you can move in the 4 directions. Oh man, come on, go faster. Go. I just turned the speed all the way up. Okay, so it produced that path. You might say, why does it produce that? I think it's because you can walk diagonally in this model or something. So technically, it looks like, that does not look like the shortest path, does it? But it's the fewest steps. Like diagonal counts as a step. So technically, walking straight down is the same number of steps in this model. And then diagonal. Trust me, that's the shortest. It's equal to the shortest path in this model. But okay, let's do Dijkstra. Dijkstra's algorithm, I think you remember, instead of jumping out in a square, it doesn't like to go uphill. See how it's kind of avoiding going up this hill here? No, I don't want to. It goes up a little, but see how it's kind of going around the hill a little bit? It's got this weird like Millennium Falcon approach shape kind of thing going on here. Go faster, go. I think it looks like moss or mold or something growing. It's kind of cool. You could do it. Found it. So it didn't draw the path. I don't know why. Whatever. But it visited actually not much different number of squares than breadth first search, but you could kind of see the order it was going in. It really didn't want to go up those hills from a dark place to a light place, right? Okay, but it visited 3,600 squares to find that outcome. Let's look at A-star search on the same graph. Look what it's doing. It's really going around that high spot. Look at that. Let me go around the low ground here. See that? It eventually goes up there a little bit, but this other path is way ahead because it was cheaper to avoid those hills. So it goes a little, it goes a little. You could definitely see it doesn't fan out quite as wide. It's really kind of like trying to make a beeline for the goal and only not doing that if there's a hill in the way, in which case it stops to look a little bit around. So I don't know what, I think it's going to come around the side here. Look out. It's going to get you. Oh. Anyway, it found the same path with the same length and the same cost, but in order to find it, instead of visiting 3,600 locations, it visited 1,600 locations. So that's like way, way, way faster. For this kind of data, A-star is much more efficient. So that's why I used A-star for my ghost, because that means the ghost would try to go to Pac-Man by going straight at him first before it explores going off some crazy other way. It just makes my game not stutter as much and not be as slow. So yeah, that's A-star. Any questions about it? Is there a question? Yeah?
Is there a standard way to break ties in this algorithm?
To break ties, like tie for the priority or the cost or something like that? Well, the good news is the priority queue will do that for you. If you put in 2 elements into the PQ that have the same priority, it'll just put them into the heap. You guys learned about the heaps, right? So it'll just put them in, and when you dequeue them out, it'll just dequeue them out the natural order that they come out. And basically, the tie breaking is taken care of for you by the priority queue, so you don't actually have to worry about it. It'll be okay.